Good afternoon, everyone. Welcome to another seminar of our seminars of the astronomy department here at the IAG. Many thanks to be here with us. Today is our last seminar of the semester, and we will restart the cycle on the last week of July. So stay tuned. And today I'm really glad to present Amanda Lopes here. Thank you very much for accepting our invitation to present your work here today. And I will very briefly introduce her. She holds a bachelor's, master, and PhD in astronomy from the Universidad Federal de Rio de Janeiro and has held postdoctoral positions at the Observatorio Nacional at the Institute of Astrofísica de La Plata in Argentina. And currently, she's a postdoc here at the IAG-USP. So Amanda, whenever you're ready, you can start.
Thank you for the invitation. I'm glad to present a little bit of the work that I've been developing here, and that started in my last postdoc in La Plata. And one thing that I want to mention is that the title is different because I overdid it with the size. It was too large. I have no idea what I was thinking when I created the title, so I kind of shorted a little bit. And another thing to draw attention is that I put it here in red, Fornax-Dorado, because the results that I'll be showing, it focus on that. So, but as Eridanus is part of the whole complex, the whole substructure, I kind of added here for a general context. And the collaborators, I have here mentioned a few of the collaborators involved with this work, but there are many more from the S+Fornax project collaboration, which is a great collaboration. So I would like to advertise here if someone has interest in whether from simulations, using simulations or observations with Fornax. It's a great group to interact. So you're publishing some papers now in the last few years. So if you are interested in that, please get in touch with me and I can point you to the right people. So there is many things in the title. One of the first things that draws attention, at least to me, it's the large scale structure. So what exactly is the large scale structure? One way of thinking this comes directly from the observations. And this has been seen from CFA from many decades already, from CFA to DF. Here I have some this low one, which is very well known, and more recently DESI, which basically is here shows the distribution of galaxies. This is a redshift distribution, so you don't have only the information from the spatial position of the galaxies, but you also have the redshift, which means the distance from us. So, and you can see in both cases here, it's pretty clear that the galaxies, because here each one of these, it's a point, it's a galaxy, and you can see that they are not randomly distributed. They seem to form a pattern here, which it seems like a web, and that's why it's called the cosmic web. And as I'm going to mention here over and over again, a lot of the names in astronomy, it's kind of straightforward. So cosmic web, it's literally because it looks like a web, and it is cosmic. It's literally astronomers given names. So, and some of and more recently, you're trying to understand better the elements of this cosmic web and the nodes where you do have a lot of galaxies. It's called the nodes are the clusters of galaxies. Some small nodes are the groups. And here, for example, you can see there is a system of galaxies that can be a cluster or a group. And you also have some kind of pathways that form this web that we call the filaments or bridge, depending on it. That is the connection between these structures, between a cluster and a group of galaxies, or between groups of galaxies, or between a cluster and a group. So they are called filaments and bridges. And you also have, it's not pointed here, but you also have some underdense regions that it's called the void. You see that a lot in the simulations, and here you have a dark matter image of that, and then you can also see it somehow with the gas, with the galaxies. And when you try to trace with some codes, and I'm gonna mention a little bit, I'm just gonna mention that you can kind of try to detect this filament, the connection between them, the filaments with some codes that I'm gonna mention. And here are the traces of these filaments. And you have a lot of work being done, in particular with the simulations, but also we are starting to move in this direction with the observation as well. And let's talk about specifically one of the superstructures that I'm actually interested in here today. That is the Eridanus-Fornax-Dorado complex, can also be called the Fornax wall. It's been known for some time. It has different names. It's part of the southern supercluster. More currently, they call SSCA because it's a strand of the southern supercluster that divides in two. That's a lot of names here, but the point is it is a huge complex in the sky that connects three main structures, which is the Fornax cluster, which is here. You have the Fornax cluster, which is the main element of this substructure. You have the Dorado group, and you also have, here it's called cluster, but it's a supergroup, because you can actually see like the supergroups together, and here you can actually see an example of this, that it's not exactly like the Fornax cluster that's showing here, which is more well behaved per se in the distribution of galaxies. In the case of Eridanus, it's not. You do have like many groups together. And a lot of work has been done with that. And like I mentioned, now we are starting to move from the simulations with the observations, kind of following the same path. And one of the most recent results regarding of trying to detect, of better understanding this whole complex has been done by Raj, 2024, where they use a catalog of galaxy groups, which means that it is a spectroscopic sample, and I think it's important to mention that, because a lot of things that I'm going to mention here, it's based on spectroscopic sample, which means we're not talking about complete samples here. Just to make this disclaimer, and you will see that's pretty clear that we may be losing some galaxies here and there. So the picture, it's not full. It's not so easy to understand. But what they did in this work, they used this catalog of groups and galaxies, and there is a code called One Dream that uses the closest neighborhood with PCA. It's a mix of these two approaches to try to define the filaments that connect the three elements: the supergroup, the cluster, and the group, and the Dorado group. So their results, the main results, that they actually find a main substructure, a main filament that could connect all of it. Actually, it's a mix of several segments of filaments that kind of connects the three things, the three elements. And the radius is quite big. It's 3 megaparsecs here, as you can see. And people that work with that already been told that this is too much. It's not my work, so I don't know. I'm trusting them here. So I'm not going to discuss how valid it is, but they actually find this result. And this is important because I'm going to be using this Fornax wall or this spine, the connection that connects the three elements of the complex. I'll be using this in plots from the results. So it's important to know that this is based on observation. And additionally, what they do find is that closer to the spine, to the main wall there, as close as you get to the wall, you have more early type galaxies. And when you go further away from the main spine, and I'm not saying closer to the cluster, because of the main spine as well, you do have more late type galaxies as you go further away. So that means that the filament is actually doing something with these galaxies. There is some kind of processing going on there. In here, as you can see here, as far as you go, you can see exactly what I mentioned here, that it drops the early type, and you have a little bit more of late type galaxies. And so, associated to this, we were going to try to make a connection between the morphology and how the environment changes the morphology. So it's important to mention a little bit of the environmental process that can go on in the galaxy, because as I mentioned in some other seminar, galaxies suffer a lot. They've been through very difficult things. They pass through harassment. A very dense environment is a very difficult element for a galaxy. They have their gases stripped, which means they do not form stars anymore, which for a galaxy, it's the end of the world. If they cannot form galaxies, what will we do? So it's a problem from them. So you have many different physical processes that are going on in thinking about a dense environment, thinking about a cluster, thinking about a group. So we already know that. So this is being already shown a lot in dense environment. So, and it makes sense because you have a lot of galaxies together, of course, that they will impact them. In here also, it's a little bit more physics here, that depending of how the galaxy is starting to get into the cluster environment, it can pass through a lot of things. And we can have the mice, quenching, gas stripping, like I mentioned, starvation, mergers, interactions, and all that changed the components in gas, in stars, in mass, in many different ways. So it's really important to understand how this process happen in the galaxy, but this is not being much discussion in environments such as the filaments here, the connection. And like I mentioned, in simulation, it seems like it is important, but in observations, we still are trying to get a better feeling of how this happened. So, like here, it's one interesting result that the authors mentioned, that depending on how the galaxy gets into this filament, this connecting filament, they pass through different pathways. It can be from the field and then gets into the filament, or they can actually get into a group and the group gets into the filament, or they can actually get together within the filaments into a group. It's a different pathways, and all that affect how the galaxies, what happened to these galaxies. And from the simulations, they actually find that it is a mixed bag. It's not very clear if you don't have only one pathway. It is being seen in the simulations that you actually have a mixed bag of things in filaments. So filaments, we don't really know still what's going on. Here are some also results regarding to this. And you can actually see that this other work using the 300 simulations. The other one, I think, was TNG. This one, it's the 300. They also see that a lot of galaxies in the outskirts of clusters, they have a 45% of being the filament, so it's a good amount of galaxies in the filament. And some of them are in groups. Some of them are black splashed, which means they get in, they get out. And some of them are just in the filament. So again, a mixed bag of things. Here it's a work done with the observations in this regard. Like I mentioned, there's been some effort of trying to better understand what's going on within the filament with observation as well. This was done with slow-on data. And they also see something similar that's in the simulations, that you do have, as you go closer to the spine of the filament, closer you get to the filament, to the bases of the filament, more early type galaxies you get. So it seems like they quench the star formation. It's being pretty clear. So, and thinking about this whole scenario, what are we doing? What type of work we do? So, like I mentioned, there is this big work from Raj 2014. That one also that I didn't put here, but it's where this image comes from, where they actually try to use dwarf galaxies to get a different picture of what's going on, but they are not confirmed, so they are still candidates in this. But what we are trying to do, it's trying to better understand the morphology through what we call the non-parametric analysis, which I will show exactly what I mean with that. And we focus a lot on Fornax towards the Dorado group. It's one of the reasons why it's to actually also be able to get the emission, the H-alpha maps from S+. And originally, the limit on the footprint of S+ for this area was more or less here, which means we kind of lost the Eridanus supergroup. We actually do have some images now. We asked for time, and we do have that now. But I try to focus on what it is on the survey itself. So that means working with Fornax and Dorado and things in between. Anything that it's in between. That's the reason why, the motivation. So, what do I mean with non-parametric analysis? I mean distribution of light. So, what this analysis gives us? Give us different parameters or index, I think it's better, that tells you how the light is distributed in a galaxy. And again, like I said, the names are very straightforward. One of them is concentration. It's how concentrated the light. So there's different ways to define this. In the case that I'm using here, it's with this equation, which is basically the relation between the 80%, the radius that contains 80% of the light over the radius that contains 20% of the light in the galaxy. Usually people also use 90% over 50, but it's just a definition. The main idea of this index is to tell you how concentrated the light is. We can also have a symmetry, and to obtain a symmetry, the name itself is also straightforward. If the light of the galaxy is distributed asymmetrically, for example, one way of doing this is rotating the galaxy along the line of sight by 180, and then you have an idea how asymmetric it is. You can also blur the galaxy, and you have a parameter such as smoothness or completeness, depending on the definition. And another one is Gini and M20, which are not so well known, I think. Gini actually comes from economics. I don't know if many people know, but it's used a lot in economics to tell you how uneven, for example, a a population is of galaxies, of people, is how less money people have, basically. It's very used in economics. But the idea is it's the same. It tells you how uneven a galaxy light is. On M20, tells a little bit more about the clumpiness because it tells more about the brightest. The 20 comes from the 20% brightest substructures in a galaxy. And in here, just to give an example that combining these things, how you can better understand the galaxy. If you have a high G, but a low M20, which will be something more or less like this, it is like a Bose-dominated type of galaxy. For example, if it's a high G, but in the high M20, it's going to be a merger, because if you have a high M20, that means that you do have brighter superstructures. So that makes sense that you have something like this. So putting together, the main idea is that putting together these parameters, you can have an idea of how the light is distributed, or in how the morphology, obviously, of this galaxy works. So here are some of the diagrams that can be used to assist us understanding the morphology of this galaxy. This is a very known diagram from Lopes that divides or try to give you some idea of the merger galaxies with the most well-behaved galaxies, let's say, which are the ellipticals, and that's zeros here. And in here you also have a fraction of irregulars and spiral galaxies. So this type of thing can assist you in classifying and better understanding the galaxy. And more recently, there is the combination of concentration with asymmetry to try to detect perturbed galaxies that could be potentially candidates of Ron-Price stripping, for example, from this work from Angela. So, and what for doing the part of the morphology, what we're gonna be used, it's the Daisy Legacy Image Survey. And why this? There are two reasons. It's the depth, because for morphology, an important thing is it's the depth. The deeper the image, the better to get details of the galaxy, faint structures. So you have more information on it. So the depth is important for that. But for this specific kind of work, that it's a really large area in the sky, you also need a good coverage. So using Daisy Legacy image, it's a compromise between depth and between coverage. And I mention this because in the case of Fornax, there is a survey called the Fornax Deep Survey, which comprises the central part of the cluster and the Fornax A2B group. I'm going to mention a little bit more specific about Fornax. But the point is, they only have this part. So we do not have access to what's in between, which is the goal here. So even though there are deeper data for Fornax, for the rest of the region that we're trying to assess, there is not. So far, this is the best we can do. For people who do not know, that's the legacy image surveys. It's actually a combination of different surveys here. Here I have a description. They are done in 4 optical bands. Here is the distribution, more or less, with the depth and the G image. And also mention here the results I'm going to be showing it's for the G, because we are trying to get perturbed galaxies, and for that, usually the bluish possible type of image is the best for what we want. So that's why we are going to use the blue. And the tool we are going to use for that is called Astromorphlib, which it builds upon the StatMorph code. It's very well known. And in this version, it was automatized, and it is adapted for images for legacies, low and S+. And it basically calculates the non-parametric index that we want. and also has a fit on the 2D characteristic profiles. Here, it's one, as an example, an image of an output of this code. And here is also something that he gives, which is the residual, which for us, they're trying to understand how asymmetric a galaxy is. This is very important, which is the residual image between the observed one in the characteristic model. So usually this is very important for us. And for the H alpha emission part that I mentioned, we use S plus, which it is in the internal, the 6th data release, the internal 6th data release. It's a telescope, the 80 centimeter telescope. It has 12 bands, a mix of broad and narrow bands. In particularly for me, that we are tagging H alpha at the distance of Fornax, which is 20 megaparsec. We actually use the H alpha filter. We do not need to use other for this. And for that, I made a pipeline, a pipeline that creates a cube, given you only need to give as an input the position and the size of the image. And it creates the cube and then performs a mask, which is a very, let's put it nicely, it's a very complex thing to do in the sense that it takes longer than one would like to do, but it's a very important step on this process. And then there's a background subtraction, a Butterworth filter, which is also very important because of the noise of the image, PSL homogenization. Depending on the size of the image can be rebeamed. We do have a Voronoi here, also to get the best possible signal to noise. For people who do not know what Voronoi is, basically to guarantee a threshold of the signal to noise. And finally, we get to use what we call the 3-filter method, which basically it's an easier way to get the emission line maps without doing the whole set fitting. So it's basically, it's kind of maps the excess of the H alpha filter in respect to two other filters that work to build what we call a continuum. The continuum is very simple. It follows like a linear relation between the three filters. So it's very simple to do. Yeah. And then we have the emission line map. This is from the paper from last year. In here we compared, this is the image from Legacy. This is the map done with my code. I didn't mention the name of the code, which is Pelé. And there is a reason why it's Pelé. Like Maria mentioned, I was doing the postdoc in Argentina, in La Plata. And there was, I wouldn't say a competition, but there was some friendly competition there. And because one of the PhD students that some people here know, Rodrigo, also had a code which did not have a name back then, to just say. And when I decided to give Pelé, he decided to give his code name Messi. So yeah. Well, Pelé always comes first, just to make the point here. It came first. And here you have the Muse, a map, a emission line map made with the Muse data, with Muse, based on Muse IFU. And doing some, in this paper we discuss a little bit more, but we are able to recover fairly well fluxes higher than 10 to the 7.2 plus 10 to the 17, which was quite surprising. I thought it wouldn't be that good, but it did work fairly well. I do have to make disclaimers here. This approach works really well for extended sources and for usually brighter than 18 galaxies. It is possible to do for galaxies that are fainter than 18. It's not that it's not possible, but the noise, the level with the noise, it's very competitive here. So it's not so trustworthy, but it can be done. It's not impossible. Another thing, it's the brightness of the object as well. I do have a case, I'm not going to show here, but you mostly don't see the galaxy, but you actually see one region, one region of emission very clear. So that weird cases can happen like this, but usually it's more advisable for extended source brighter than 18. And I say sources because this can also be done for planetary nebulae, for example, which is something that I play around a little bit. It can be done as well. It works pretty well too. Talking specifically about the targets here, which is the Fornax for people who do not know. Fornax cluster, it's the second closest cluster that we have after Virgo. It's not as rich as Virgo, but it's very close by. It has an infalling subgroup that's called Fornax-A. Here it's an image of some of the galaxies that belong to. Here it's the center. Here is the center of the Fornax cluster. And the sample I'm going to use here in this work, it's from Smith-Castelli 2024, which had 233 confirmed members. But that does not mean that we are able to analyze all of them. Some of them are really faint, so they were not added here. We lose about 20 members or so. And the Dorado group, for people who do not know, it's a really loose, it's rich group. It has a compact group, or some call compact group, that composes NGC 1553, NGC 1549, in NGC 1546, and IC 258. It is a little bit, it's about 18 megaparsec, but that depends on the reference. Currently, at least for the last papers that I read, they use the NGC 1553 as the center, or closest to that galaxy as the center of the cluster. There is some discussion. Some people use 1566. So, but I'm following the latest paper. Here is a distribution of some of these galaxies. This is the initial sample that was compiled based on these papers here. But okay, from literature, you do have very clearly, like I mentioned, this is from the compilation from Smith-Castelli. This is here, Dorado, you do have from a compilation from the recent papers, but what is in between? So we did a huge compilation with this area. Interesting enough, after a lot of cleaning, it was getting reduced very fast. And after a final comparison with this, we end up having about 68 galaxies in between, which I thought would be more, honestly, when I started this. But also, I forgot to mention this, that I added Fornax here, Dorado here, because I wanted to see if there was additional galaxies that could be also members of Dorado that for whatever reason were not included. Indeed, that kind of happened. Using the compilation that was made, and then with basis on this is the phase space diagram, which is the difference of which shows basically the difference in velocity in respect to the center of the group divided by the sigma of the group. I did this up into 2 R200 of the group, and we actually found 13 new galaxies. These are the new galaxies. There's some really bright galaxies here, this one, for example, which I'm not sure why was not included before in any of the other works. And in the end, what we do have for the general sample of the Fornax-Dorado, and in between, it's something like this. I forgot to mention what it's in red here. It's the distribution of the magnitude in Fornax. This one in yellowish, it's the orange more. It's the Dorado. You do have something really faint here. This was a detection using actually meerkat data, mongoose. Actually here, that's why it's very faint. But, and what it's in blue or purple here, it's the bridge. And you can see that the bridge, it's pretty much bright objects. You do have one here, 19, but most of them are in here, are above 16. So maybe we're losing some bright galaxies as well. We do not know. But this is the sample we have so far. This is the distribution of them in the sky. Like I mentioned, this is the Fornax wall from the Raj paper that I mentioned in the beginning. Here it's a zoom in on the region of the bridge that I call the bridge, which is the connection between the group and the cluster. And you can see one interesting thing just by looking at this, that you can see here I also put the galaxy that belongs to groups, to known groups. So you do see here many galaxies. You can also see something like here outside. But in the filament itself, you can also see there is two groups here and many galaxies that belong to group, which could be the pre-processing. I'm going to talk a little bit more about that. So from the paper from 2015, 2025, we are with the Pelé pipeline. We were able to map 77 emitters within 4 radio radius of the Fornax cluster, and you can see that the distribution it's not exactly symmetric. It goes. You do have some, which I'm going to point out later on, but you have some places where this is only the emitters, to be clear here. The ones that we can actually see very well. The faint ones do not have emission, but you can see here. And also one thing is that Pelé was able to map not only late, because late type it's pretty obvious that we were going to be able to map, because you have the 82 regions, the star-forming regions, which are pretty obvious. But we are also able to find emission or map emission even in late type, in early type galaxies, which was also kind of surprising. One of the main results from this paper were that without thinking about the filament, without thinking of the large-scale structure, we did find some evidence that the early type galaxies were actually should be part of the pre-processing, and they had some evolution before getting into the cluster. So, and this was even before thinking about the large-scale structure. This is the result for the Dorado. And there is a lot of emission in Dorado, way more than I originally expected as well. As you can see here's some examples, so some beautiful images here. And for the bridge, for the connection, we also have a very, very, very large number of emitters. We have emitters in groups. They are within the bridge. And also for isolated galaxies, which is something very, very interesting. Here, I'm going to show a little bit of some results for the stellar mass. Oh, I didn't put it here, but this was made with the Taylor equation, which basically use a color relation to try to map the stellar mass. I forgot to put the equation here. But it's interesting to show that if you look at the one that it's in here, that it's on the left side, you can see that the bridge, it's mostly low mass galaxies. We do have very few that are up there. But again, in here, we do not differentiate between isolated galaxies in the bridge and galaxies from groups. So in here, it's all the bridge. Here is Dorado. And here, obviously, you have the cluster. The cluster has some of the highest mass we do have in the sample. However, once we separated the group galaxies from the bridge, from the isolated galaxies in the bridge, that's when things get more interesting, because you can see that in the groups is where the higher mass are located. The isolated galaxies are mostly low mass galaxies in the bridge. And one thing to notice that you can see that in the Fornax, you do have like a really high mass there that's not in here. Here's the cluster. The reason why is because originally the sample of Fornax includes the Fornax A in falling group. And the BGG, the brightest galaxies in that group, it's extremely massive. So it's NGC 1316. It's very massive. So once it is put together with the other group, that's why it is disappeared from here. These are the parameters from the non-parametric analysis. You can clearly see this is concentration, asymmetry, smoothness, Gini, and M20. The important thing by looking at this is that you can clearly see they have completely different morphologies in all the different parameters. You can see, for example, that the bridge galaxies are mostly asymmetric. You have a lot of very high asymmetry. And I'm saying high asymmetry things higher than 0.1, for example, which is completely different from Fornax, where you have the mean, you have most of the galaxies below that, which makes some sense. Because we're talking about a cluster group, so you do have a lot of galaxies that already been evolved. And the Dorado, you do have some really high asymmetry as well, even though you do have some other galaxies who are not so asymmetric. So you have, so the point here is that the galaxies in the different separates, in the different parts of the complex have different properties, clearly. They're probably related to the environment that they are located. Doing the Lopes classification that I showed in the beginning, that's one of the things that we can do with these parameters. We do see here that for the isolated galaxies, we have a lot of late type galaxies. For example, you have a good fraction of merger type galaxies as well, even though they are isolated, which is puzzling. And you have a slightly lower fraction of more early type like galaxies here as isolated. Yeah, in the cluster, you do have a little, it's the one that has the most late type galaxies, early type galaxies, which also makes some sense. But this here is something to investigate still. Here's the projected phases diagram, thinking about the whole sample. And in here, it's clearly, you can see more clearly that the groups, this group here, it's Fornax A, that it's around 2. It's between 2 here, 2 R200. But there is an excessive number of groups here, of galaxies belonging to groups between 4 and 6 R200, which is pretty much showing what we call preprocessing, which are the galaxies, again, are getting within a group, and they are getting processed there, getting evolution, and then falling as a group within the cluster. The connection, one thing that is also striking is that connection with Dorado, it's not so strong. We do not have many galaxies here, which is one of the things that bother me personally, because I wish I had more galaxies in this to get a better connection, but that's what we have so far. Like I say, complete is not something that I'm gonna talk much here. And we can also put everything together, that diagram from lots that we do have the merger classification. We can also do some asymmetry, anything that's higher than 0.1, for example. And when you put this, you have a lot of asymmetric things all over the place. So it's not so clear, but it's definitely clear that in the bridge, which is this region here, we do have a lot of asymmetry going. Here's another way of seeing this, is in a sky plot that I think it's easier to see that there's a lot. Even for isolated galaxies. Again, in groups, I could foresee high asymmetry. But for isolated galaxies, obviously, asymmetry can be due to many things, including some irregular galaxies. I undoubted that there is some in this asymmetry here. It is due to being irregular, for example. But still, it's a really high fraction, which was not something that I originally expected as well. One thing to comment is that filament that Raj made in his paper, it doesn't pass through the center of Fornax. It passes kind of on the side. And interesting enough, it's when you have a lot of asymmetric galaxies. This is from my paper from 2025. You also have a lot of emission line galaxies, exactly where it passes the wall, let's say, the filament that connects. Another interesting result that we're still discussing, and that's why I try to be as careful as possible, because I'm not saying these are jellyfish galaxies, please. I'm not gonna say this. First of all, because they are in the bridge, they are not within the cluster, these are not within known groups as well, so they're technically isolated. So, but they do have some similarities to non-jellyfish type galaxies, which is very curious. Again, why are these? And you can see this one particularly, you can see there is a lot. There is like almost like a tail for here. So again, what could be an explanation for this? One of the explanations that are in the literature, it's the possibility that we do have some gas stripping, some things are going on within the filament region, especially for low mass galaxies, which is interesting because my galaxies are exactly the low mass galaxies as well. So it could be that there is in simulations a scenario where, depending on the infall time of the galaxy within the filament, which means depends on how long the galaxy fall within the filament, we do have different processes going on, and that they could be the reason why the galaxies are asymmetric. And they do find asymmetric galaxies within the filament. So it's quite interesting. Another thing that I'm just going to pass for here, but I would like to mention, it's the alignment with the BCG. It's something we are working on it with Leah. So I would like just to show that we are doing this. We still do not have a clear result. We do see, for example, these are the red galaxies that were classified using something like a color classification such as this. They do have some kind of alignment towards the BCG, but it's not so clear. There's still a lot of work to be done in understanding this, but it's something that we are aiming to do in the future. And the message that I want to leave here is that filaments, they do matter. They, even though they are low mass, they do have impacts on the galaxies, and it's really important to know, to better understand how the galaxies shape. So, thank you.
Thank you very much, Amanda, for this great talk. Let's start with the questions over here.
Hi, Amanda. Thank you. Hello? Can you hear?
Yep.
Thank you for the talk. Very impressive, all the measurements you made. But I have a point on the general idea of the project. Because when those kind of morphology studies were made in the 80s and the 90s, they are most concentrated on clusters because they already have a lot of galaxies in a very small space. And they have a doubt and a debate whether morphological changes would depend on the distance to the center or the local density. As time went by, those studies went to the field galaxies, and the local density won. It physically means that the local processes of galaxy-galaxy interactions would be the most important. However, everything in the structure of your project completely disregards local density. It all comes back from the distance to the filament, and is it in this group, is it in this other group? And besides not talking about the density, then you have to bin your galaxies. You have to tell, this is in the bridge, this is in blah, blah, blah. It means putting boundaries, which sometimes they are really sharp and you can see, sometimes they are fuzzy. And then when you use like a variable like density, you can do an analysis that precludes bidding. Okay, in my view is always something we look for.
No. I see your point, and I didn't mention much about density, you're right. Also, one of the things that it is discussed in the literature, it is the density of the filament as well. Because I didn't mention this, but in this particular case, the filament is not so dense, which is another problem. We do have many problems in this, a lot of limitations, but I understand what you mean. And it may be a good pathway to do something like that. Yes. I see.
Okay. They will, yes. I forgot about that.
You said that in the outskirts of Fornax, you find a region where there's more emission line objects, there's also more disturbed objects, and that's exactly where the filament goes. Can you separate between interacting galaxies and jellyfish galaxies of these objects, or you have never tried to do such a distinction?
No, I haven't done this type of distinction, but it could be interesting to do. You have a point there. Yeah. Yeah.
When you say that you cannot decide if these are jellyfish galaxies or not, what do you call them then?
That's why I say jelly type, in the sense that they look similar to, but it's really hard without the radial data to actually confirm this. Honestly, I don't know.
More questions? Thank you. More questions? Yeah. Slide 10.
Your slide number 10.
Okay.
I think it's number 10, I don't know. It was in the beginning of the talk. You showed the fraction of early types and late types against something. I think it was the radians.
Okay.
And they didn't add.
Was that one?
No. In the beginning.
Okay, in the beginning. Oh, okay. In the.
You had early types and late types, and I was just curious because they did not add up to 100%.
Right?
Yeah, that one. Yeah. They are fractions, but they don't add close to. Is there anything else between besides early type and late types, because they do not add to 100% there? Or maybe these are the numbers.
That's a very good point.
Maybe these are the number of galaxies, not fraction.
Yeah, maybe around.
Yes.
Yeah. I don't know.
And also, if I may just mention, it occurred to me, I mentioned to Angela here, that an analogy to understand pre-processing is that, people are going to a party in the center, in downtown, the cluster. Some people go by themselves, others go in groups.
Yeah.
And if you're in a group, you have your own booze, you're already drunk by the time you get there, that's pre-processing.
Yeah.
You get to the party like, half drunk already. Should be explored in the future.
I will use it in the future. Thank you.
Do we have more questions? No? Beth? Beth? Será que ainda está por ali? Beth? Não sei. Ok. Não sei. Não sei se deixamos para depois. Okay, I have several comments on the names of your codes, but we can discuss during the coffee break. So thank you again. Thank you very much, Amanda. Thank you.
Oi? Por que não se chama Neymar? Sério? Eu preciso explicar? É necessário?
Eu tinha perdido a conexão. Foi Maria Vitória. Maria Vitória.
Não tem galáxias próximas, elas são isoladas. Quando eu digo isolada mesmo. Eu não gosto nem de chamar essas aí de candidatos, porque elas não estão nem no ambiente de alta densidade. Como é que eu vou chamar isso?
Não, mas é que eu acho, porque assim, não, quando
Posso fazer um comentário rápido?
Para ela sofre uma room pressure menor, né? Entendeu? Mas aquele elas têm, mas ela deu uma room pressure menor.
Maria Vitória.
Então elas também não precisa ter tanto, assim, também são mais lá.
Vocês conseguem me ouvir?
As clássicas, que a gente mais conhece na literatura, né? Elas estão mais próximas do centro.
Mas é o que eu falei, todas essas que eu mostrei, todas essas pseudo-candidatas, aí elas são todas abaixo, inclusive, abaixo de 10, acho que abaixo até de 9,5. 10 a 9. Elas são bem baixas.
Sim, mas a simulação, nós procuramos as simulações baixa massa e mais baixa. O Richard, o paper dele também tem fora do volume.
Maria Vitória? Tem alguém me escuta? Deixa pra lá, deixa quieto.